We want to evaluate the triple integral over the region E, where E lies between the spheres given by x squared plus y squared plus z squared equals 2 and x squared plus y squared plus z squared equals 25 in the first octant. Let's first look at the region of integration in space. So the region of integration, the region E, is this solid region here bounded by these two spheres in the first octant. And because the region of integration is bounded by two spheres, it's going to be easier to use spherical coordinates to evaluate the triple integral rather than use rectangular coordinates. So going back to our work, to write a triple integral from rectangular coordinates to spherical coordinates, we first have to write the integrand function f of x comma y comma z as a function of rho, phi, and theta, and then differential v is equal to rho squared sine phi d rho d phi d theta. So notice how we have an extra integrating factor of rho squared sine phi when converting from rectangular to spherical coordinates. So in spherical coordinates, we'll have a triple integral. Notice f of x comma y comma z is this rational function here, which we must write as a function of rho, phi, and theta. And because x squared plus y squared plus z squared is equal to rho squared, we can write this as 1 over rho squared. And then we have the integrating factor of rho squared sine phi. And then we have d rho d phi d theta. And we're integrating over the region E. So before we determine the limits of integration for rho, phi, and theta though, let's simplify the integrand function. Notice how this simplifies nicely to just sine phi. Now let's determine the limits of integration for rho. For review, in spherical coordinates, rho is the distance between the point and the origin. Notice rho is labeled here on our graph. So to help us determine rho for the region E, we need to consider this distance here between the two spheres. Notice at this point, we would be 2 units from the origin because that's the radius of the smaller sphere. And at this point here, we'd be 5 units from the origin because 5 is the radius of the larger sphere. So if we recognize this, we now know the limits of integration for rho are from rho equals 2 to rho equals 5. If we don't recognize this, we can actually determine these limits of integration using the equations of the two spheres. Well, remember, x squared plus y squared plus z squared is equal to rho squared. So we can write the equation of the smaller sphere as rho squared equals 4, and therefore rho equals 2. And the equation of the larger sphere would be rho squared equals 25, or rho equals 5. Notice how this would also give us the limits of integration for rho. And now let's determine the limits of integration for phi. In spherical coordinates, phi is the angle between the positive z-axis and the point. So in order to trace out this solid region in the first octant, phi would be this angle here, which would be from phi equals 0 radians to phi equals pi over 2 radians, which gives us the limits of integration for phi from 0 to pi over 2. And then finally for theta, in spherical coordinates, theta is the angle counterclockwise from the pole or positive x-axis in the xy plane. So again, to trace out this solid in the first octant, angle theta would start here along the positive x-axis and rotate here to the positive y-axis. So from here to here, theta would be from 0 radians all the way to pi over 2 radians, which gives us the limits of integration for theta from 0 to pi over 2. Now let's evaluate this triple integral on the next slide. So we first integrate sine phi with respect to rho, so we treat sine phi as a constant, and therefore the antiderivative is just going to be sine phi times rho, or rho times sine phi. So big F of B minus big F of A is just going to be 5 sine phi minus 2 sine phi, which of course simplifies to 3 sine phi. And now we integrate with respect to phi. The antiderivative of sine phi with respect to phi is going to be 3 times negative cosine phi, or negative 3 cosine phi. So big F of B minus big F of A is going to be negative 3 cosine pi over 2 minus negative 3 cosine 0. Well, cosine pi over 2 is equal to 0, so we have negative 3 times 0 minus negative 3 times cosine 0 is equal to 1. So this simplifies to 3. So the antiderivative of 3 with respect to theta is just 3 theta. So big F of B minus big F of A is going to be 3 times pi over 2 minus 3 times 0. So the exact value of the triple integral is 3 pi divided by 2, or as a decimal approximation, we'd have approximately 4.7124. I hope you found this helpful.